Be back in a second.
Hello.
Good morning. Okay, good morning, everybody. Let's see. I have posted your this week's homework to Blackboard. It's a little bit long. And okay, the homework assignments are designed to be worked on throughout the week. You're not really supposed to wait until Friday to start them. Okay. Yeah, and if you do wait until Friday to start them, sometimes you don't have enough time to do them. So make sure you go ahead and get started on those things. Your this week's homework, you're going to find higher derivatives, so first and second derivatives of some functions. Do some implicit differentiation. Okay. Gave you a couple of velocity problems, well, actually 3, because I never gave you any before. And also a problem where you're asked to find the equations of tangent lines. And then the next thing, what we're going to cover today, is something called related rates. So we're starting to use derivatives to do things. Any questions before we get started here? Okay, let's get started. Okay, so we're going to talk about related rates. Consider the following problem. Water is drained out of a conical tank. Okay, so you've got this big tank and it's full of water, and you pull out the stopper and the water starts to drain out. Then the volume of the water in the tank is given by V equal to pi over 3 r squared h, where r, h, and v are all functions of time. Okay, so this formula is just the volume of a cone. Given the radius and the height of the cone, the volume is pi over 3 times r squared h. But in this case, okay, we're thinking about not the tank itself, but we're thinking about the water in the tank. And if you're draining the water out, the volume of the water in the tank is decreasing. So is the height of the water in the tank and the radius of the water in the tank. Here's my little illustration. Okay. This would be, say, the water at time t. Okay. And the water is coming out on the floor or something. But the situation here is that the volume of the water in the tank is a function of t. So I've written V equal to V of t to emphasize that. This volume is changing over time. The radius is a function of t. Remember, the radius is, okay, would be that length, and the height at time t would be that length. Okay, so these are all changing with times. The volume, the radius, and the height. They're all functions of time. Okay, so we're going to take this formula, and now V is a function of t, r is a function of t and h is a function of t? Well, we can differentiate, okay? So dv dt then is the derivative of, okay, v is pi thirds r squared h. So this derivative with respect to time, dv dt, is equal to the derivative of pi thirds r squared h with respect to time. Now I'm going to start using my differentiation rules. Well, one rule says that I can pull a constant out. Okay, that constant right there. So pull out the pi over 3. And then I need the derivative of r squared h with respect to time. Okay, well, r squared h, that's a product on one level. So I have to use the product rule. Remember, r and h are functions. Okay, so product rule says that the derivative of r squared h is the derivative of r squared with respect to t times h plus r squared times dh dt. This is just the product rule. Okay, well, I still have, instead of just r, I've got r squared in there that I need the derivative of, but that requires a chain rule. Okay, this is chain rule. But I have a function squared. So the inside function is r, and the outside function is the squaring function. And that means the derivative of r squared is 2r dr dt. Okay, and that does it. That's how, okay, these two quantities are related, or these two derivatives. This is why you call them related rates. dv dt, dr dt, and dh dt are related by that equation. Okay, any questions so far? All right, then let's change it to a specific problem. This was kind of general. Suppose that the height of the water level is changing at the rate of minus 0.2 foot per minute. Seems like I got this straight out of your text, actually. I rarely look at it. That ought to be feet per minute. And what's that talking about? The water level. Well, that's talking about the depth, H. That says, this sentence says that dH dt is equal to minus 0.2. Okay, right from there. And why is it minus? It's minus because the volume is decreasing, the height is decreasing, and the radius is decreasing. Well, the dH dt is negative because the height's decreasing. The radius is also decreasing, okay, right here. So this says that dr dt is minus 0.1. And we want to know what is the rate of change of the volume when the radius r is 1 foot and the height h is 2 feet. Okay, well, r equal to 1 and h equal to 2, this is at one moment in time. over time, R is decreasing. Over time, H is decreasing. But at a particular moment in time, R is 1 and H is 2. It looks like in this problem, the rate of change of the height is constant, minus 0.2, and the rate of change of the radius is a constant, minus 0.1. So this holds, these two things hold over the process of draining the tank. This only holds at one moment in time. But then we can get the rate of change of the volume. Okay, and let's write what we had computed before. Pi over 3 times 2 r dr dt h plus r squared dh dt. Yes. Okay. Okay. So that's our general relationship between these rates. But we're going to put in 1 for R, 2 for H, dr dt was minus 0.1, and dh dt minus 0.2. Okay, yeah. Okay, so that says that dv dt is pi over 3 times 2rh times dr dt plus r squared times dh dt. And that's equal to, let's see if I'm up to the arithmetic this early in the morning, pi over 3. That's 4 times minus 0.1, so that's minus 0.4 plus, and it's, remember that pi over 3 goes with that second term 2, times minus 0.2, which is, okay, pi over 3 times, distributed it because I'm undistributing it now, which is pi over 3 times minus 0.6. So I guess I could divide out a 3. That's minus, and that would be times 0.2. It's a minus, not a decimal. So dv dt is minus 0.2 pi. Will be cubic feet per minute. Per minute, yeah. When r equal to 1 and h is equal to 2. Yes. Okay, and again, volume is the rate of change of volume. Rate of change means derivative, remember. Rate of change of the volume is negative because the volume is decreasing. Any questions?
Would it be possible for us to go over that same question with sort of with different R and H values, please?
Sure. Let's see. Well, we
I think he's asking you to show a problem that's a little easier to follow along with.
I thought this. Okay.
Actually, I understand what you said. I was just wanting to perhaps see how it would compare with, say, if R was 2 and H was 4,
Okay.
for example.
Okay. Well, this may be a different tank altogether. Okay. So to some extent, these depend on what tank, but okay. So you want R equal to 2 and H equal to 4. So change. Okay, we can do that. And let's see. I have to remember my basic related rate equation here. Okay, so it was pi over 3 times 2RH dr dt plus r squared dh dt. Make sure I do that right. Okay, we're going to keep dr dt at minus 0.1 and dh dt at minus 0.2, right? Okay, so if we make that change, R is 2, H is 4, dr dt is minus 0.1, r squared is 4. Well, I'll just leave it as r squared for the moment so you can see where it comes from. 2 squared, and then dh dt is minus minus 0.2. Okay, so that would be 2 times 4 times 2 times 2 times 2 is 16, right? 16. Plus 4 times. And 16 times 1/10 is 1.6. And 4 times minus 0.2 is minus 0.8. So that's going to be minus 2.4. So if that's true, then dv dt is, and I could divide out 3 from that too, minus 0.8 pi minus 0.8 pi cubic feet per minute. Does that help, Mr. Levy?
Yes, ma'am. Thank you.
Okay. Yeah. I remember when I was a student, I thought these were so hard. But you'll get comfortable with them, all right? If you work the problems. Let's do another one. Okay. Here's another example. Air is being pumped into a spherical balloon. So that its volume increases. Oops. At a rate of, okay, this is volume, so this is going to be cubic something. Let's see, what are our units? 100 cubic centimeters per second. Okay, so you're given dVdt here. We would like to know how fast is the radius of the balloon increasing. When the diameter is 50 centimeters. Okay, so we need to gather things together here. This balloon, you're pumping air into it and it forms a sphere, okay, this particular balloon. And as you pump more and more air into it, the sphere is increasing in volume. Volume is a function of time. You also have, well, okay, what's the volume of a sphere? We need to know that basically. The volume of a sphere V is equal to 4/3 pi r cubed. We're going to be able to derive this later in the semester, so you don't have to take it for granted. But yeah, this is the volume of a sphere, okay, that equation. Okay, but this sphere is changing in volume. Volume's not constant. It's the volume is increasing, which means the radius has got to be increasing too. Okay, so how are yeah. V is changing, volume is changing, so it's a function of time. The radius is changing. The radius is a function of time. So your underlying variable here or independent variable is time. Okay. Volume and radius depend on time. Okay. So this is what we're going to be differentiating with respect to t. Let's do that first. You don't want to put in your constants too fast. Sometimes a quantity is constant and you can put that in, but okay, this 50 centimeters, that happens at one moment in time. And if I put that in for, well, okay, that's diameter, so the radius would be 25 centimeters. If I put that in now for R, I would change volume to a constant, and it's not. Okay, so now I need to differentiate. Then dV dt is the derivative of 4/3 pi r cubed with respect to time. 4/3 pi is a constant. We know we can pull constants out, multiplied constants. So then I'm left with taking the derivative of r cubed with respect to time. Well, r cubed, that's a function cubed, not just a plain old independent variable. It's a whole function that's cubed. And that means I have to use the chain rule. Okay, so sorry. Oh, that's a lot of stuff. This is equal to 4/3 pi times 3r squared dr dt. Inside function is r, outside function is the cubing function. And may as well clean that up a little bit. That's 4 pi r squared dr dt. That's our basic relationship between our rates. The volume and the radius are related. And their rates of change are related. Okay. The rates of change are related by this equation. Questions? Okay. Well, now I put in my specific information. We want to know how fast the radius is increasing when R, yeah, this says R is 25, right? The diameter is twice the radius. So this piece of information gives us R equal to 25. And we also have, okay, this piece of information. This says that dV dt is 100. And I do have units here. This is centimeters cubed per second. And R equal to 25 centimeters. Okay. All right, so R is 25 and dV/dt is 100. And for the moment, I'm going to leave off my units. So 100 is equal to 4 pi times 25 squared dr dt. And that says that 100 over pi times 4 times 25 times 25 is equal to dr dt. 4 times 25 is 100, so I'm going to cancel those out. And I have 1 over 25 pi. So when R is 25 centimeters, dr dt is 1 over 25 pi centimeters per second. And these rates of change are positive because the volume is increasing. Questions? Okay, let's try another one. So we have a balloon being blown up and a conical tank being drained. How about we do some drivers? Okay, so here's another problem. Car A is traveling west at 50 miles per hour. And car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A, let me write this down, is 0.3 miles and car B is 0.4 miles from the intersection. Okay. Maybe if I display it, I'll make it easier to find. Okay. Well, pictures help a lot. One car is traveling west and the other car is traveling north, and they're approaching an intersection. So I'm going to put car A here. And car B there. And car B is traveling like that direction, and car A is traveling that direction. What basic relationship can I use here? And a hint. The dotted line would represent the distance from car A to car B. Anybody?
Someone in the chat just said Pythagorean.
Okay, yes. Whoever said that, very good. Yeah, you got a right triangle here, so maybe the Pythagorean theorem can help. Let's call, okay, remember, again, these things are changing. Let's call the distance okay, so let me erase it. Let x equal the distance of car A to the intersection. At time t, so x is changing, so x is a function of t. So I'm going to put an x there, x is equal to x of t. And let y equal to the distance of car B to the intersection. So this would be y. And again, at time t. Y is a function of time. X is a function of time, y is a function of time. And the distance to the intersection of car A is decreasing, right? The distance to the intersection of car B is decreasing. So X and Y are changing with time, but the distance Yeah, well, let's let z equal to the distance between car A and car B at any time. So z is a function of t also. So this is z. I don't know how I managed to change the color. Okay, so x is a function of t, y is a function of t, z is a function of t. Over time, x, y, and z are all decreasing. Well, until we go through the intersection and the problem changes completely. But okay, so basic relationship. It's just x squared plus y squared is equal to z squared. But x, y, and z are all functions of time. X, y, and z are all changing. Okay. So let's differentiate the left-hand side. Okay, the right-hand side. And okay, I've got the sum of two functions on the left, so I can break it into the sum of the derivatives using my rules of differentiation. And now, okay, x is a function, so x squared is a function squared. Inside function is x, outside function is the squaring function. Chain rule, we have to use chain rule. So 2x dx dt, that's the derivative of x squared with respect to t. Derivative of y squared, were all the same basically, with different letters. Okay, so there I have my relationship between these rates of change, and I can divide out the two, the whole thing. X dx dt plus y dy dt is z dz dt. Okay. And I think that once you get here, the hard work's done. Okay, so what's the information we put in for these values? I have to go back to the problem. Car A is traveling at 50 miles per hour. So it says dx dt. I'm not going to worry about units right now. 50 and okay, because the distance, we're talking about the distance to the intersection of the car A and distance of the intersection of car B and the distance between the two cars. These are all decreasing, so these are negative quantities. Dy dt is minus 60. Okay. And also, we have this piece of information. X is 0.3 and y is 0.4. And okay, this x and this y are only for one moment in time. I assume that their speed, well, it's worded as if their speed's unchanging. Of course, when they get to the intersection, usually you have to slow down. And usually you want to avoid a collision. So you don't want to go through the intersection at the same time. But we're not worried about that. We're worried about this one moment in time. Okay, so dx dt is minus 50. And dy dt was minus 60. And x was 0.3. And y was 0.4. Okay, and that's equal to z dz dt. Okay. Well, let's see. What I want to find dz dt, right? That was what the question asked. Yes. So we want to this. If this is asking for dz dt. That's that question. Okay, which means I've got to address what z is too. I want to know what this is, but that means I got to know what that is. Let's see in a minute here. Let's see. 0.3 times 50 is 1.5. Arithmetic. 5 over just 15, right? Minus 15. And times 60. So that's 24. So that's minus 49. No, 39. Okay. Oops. 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 Well, how do I find z? Here's where the Pythagorean theorem comes in again. This still holds, right? This holds for every time t. So z, and this is at one moment in time. The moment when car A is 0.3 miles from the intersection and car B is 0.4 miles from the intersection. So 0.3 squared plus 0.4 squared is z squared. And that's 0.09 plus 1.6 is z squared. And that's 0.25 is Z squared. And fortunately, these numbers work out nicely because the problems was rigged so that you come out with nice numbers. In real life, that rarely happens. Okay, square root of 25 is 5. So at this moment in time, Z is 0.5. You have X is 0.3, Y is 0.4, Z is 0.5. Okay, so we have a value for Z. So minus 39 is 0.5 dz dt. And I hope all my arithmetic was correct up there. We will see. So that's 1 over 2. So this should be 2 times minus 39 is equal to dz dt, which is minus 78. I guess that makes sense. Yeah. Okay, so the cars are approaching each other. This was miles per hour. That's pretty fast. Any questions?
Yes, I have one.
Okay.
Yeah, whenever you got negative 39 is equal to 0.5 dz dt, and then it went to 2 times negative 39 equals dz dt. What happened right there?
Well, 0.5 is the same thing as 1/2. Okay, so, and that means that I should multiply both sides of the equation by 2 to get rid of the 0.5.
Okay. Okay.
Okay, this thing, it'd be the same thing as dividing 39 by 0.5. Exact same thing. Okay.
Yeah, I got it. Thank you.
Okay, so these problems, well, what do you want to do? You have to take each problem on its own. Okay, there are going to be different situations, they're going to have different relationships involved. I would say read the problem carefully, draw a picture, figure out what your basic relationship is, figure out what information you are given, and then go from there to figure out how you can get to answering whatever the question is asking you. Do we have time? No, we do not have time. It's 8:54. Okay, we'll do some more of these tomorrow. Okay, but one thing that would really help is go ahead and get started on your homework. Go ahead and start trying these things for yourself. That's when you really learn, when you do them yourself. Okay, so
Okay.
I'll see you guys tomorrow.
See ya. Oh, and by the way, did anyone see my comment in the chat?
I will look at it.
Yes, I did.
I had to say that when I got that one like yesterday,